Okay, welcome back, everyone. We need to get started with our next presentation. So, a few years ago, there was an exhibit at the Whatcom Museum. It was in Bellingham, and it was highlighting mineral localities in the Pacific Northwest. It was a great exhibit, a great museum, and that was just a one-year experience. It's come and gone. Opening that exhibit, Randy Becker. Closing.
Closing.
Oh, okay. Closing that exhibit, Randy Becker, our next speaker, gave a presentation about all those deposits and a summary of localities in the Pacific Northwest. So, Randy Becker is a retired systems engineer from Boeing in Seattle, and lives in Yakima now, and he has been collecting in the Pacific Northwest for many years, many decades, 50 years. I wasn't going to say, thanks for volunteering. So I'm just going to not take up any more of Randy's time and hand it over to Randy.
Oh, good morning. I hope everybody's here that wants to hear it, because I hear a lot of activity next door still. As Julian indicated, title of this talk is Cascade Crystals, and I did develop it and give it as part of an exhibit in the Whatcom Museum. And it was quite well received, and I actually had people requested if one person actually did a vocal recording of it, and the person wanted the copy of the slides, and they're actually trying to replicate this talk. So I discussed it with Julian, and he decided that it would be a good, appropriate talk to give here today, even though this is way off topic from rare earth minerals. So not a lot of those in this talk, except for at the very end. Most of the pictures in this talk are my own, though there are slides from other individuals, and that's indicated at the top of the slide. This particular slide happens to be one of my favorite localities in the Cascades. And for those of you who aren't familiar with it, this is the Scepter Zone on Denny Mountain. I've always liked this picture because it's kind of dark and gloomy looking, which is how it's usually up there, damp, drizzly, and pretty wet usually. And those two superimposed scepters are always kind of the dream up there. Like I said, this slide also reminds me of the season, kind of a Halloween type picture. So to kind of get a feel for kind of mineral deposits where you find good crystallized specimens in the Cascades, it's helpful to look at the geologic map. But as I may not have indicated the first slide, this talk was developed for the very amateur mineral collector, hobbyist, rockhound type. And I'm sure they would look at that map and gasp and want to move on quickly. Really, the only important part to consider there with this geologic map of Washington is Cascade Range is down through here. And the southern Cascades, you notice, seems to be colored a similar color here and here. These represent andesitic, extrusive volcanic rocks and basalts. And they're not limited to the Cascades, but they do bleed over into the lowlands and into the coast ranges as well. And these southern Cascades and these volcanic rocks are characterized by the relief is very low, erosion rates are high with those type of rocks, lots of vegetation, trees everywhere, timber companies extract an awful lot of timber in that area. And so it's not what we call real rugged mountainous country, though it definitely is mountainous. From a geologic standpoint, these kind of rocks frequently host a mineral group called zeolites in gas bubbles and cavities throughout the rock. And various localities have been found throughout that area. You go further north, up in this area, approximately where Snoqualmie Pass is, the geology seems to change and it gets a lot more complex. This is what we call the North Cascades, and it's composed of many different kinds of rock masses, but typically a lot of them are metamorphic rocks, either metamorphosed sediments or volcanics, and intrusive plutons, granitic type rocks. And the North Cascades are characterized by lots of faulting, fracturing of the rocks, very high angles of relief because these rocks are very resistant to erosion, and because the elevation and everything, see a lot of glaciation. So North Cascades are very rugged mountainous areas, and the mineral type deposits you see are different. Frequently, they're associated with these areas of fractured rocks, where you get an extensive amount of fracturing of the rock, and then you have crystals forming the open space in the rock. There's also granitic intrusions in the North Cascades, and some of them have what we call myrolitic cavities, which are essentially gas, hydrothermal fluid type cavities in the granites. And if the granites form close to the surface, the pressures do not obliterate these cavities, allows them to form, and we get open cavities in granitic rocks. So this next map is a road map, which kind of correlates what we saw on the geologic map a little bit. But now we're talking about areas where localities we will look at. In the Southern Cascades, we'll visit a couple of the localities that produce zeolite minerals. And then going a little bit north, kind of in the low foothills area in here, there's Green River Gorge. We will be looking at that one. And there's a whole series of localities that produce excellent quality minerals, mostly quartz, in the Snoqualmie Pass, the Stevens Pass region. And then we will move north to the Snohomish County, Vesper Peak location, and we will end in the Golden Horn Batholith. So for those of you who aren't familiar with what a zeolite is, it's basically a generic name for a group of minerals that are all very similar. They contain calcium, sodium, potassium, aluminum, silicon, and other trace elements in their structures. Their structures are very important and pretty much common for to be a zeolite mineral. It's got to have this kind of structure, which is dominated by channels and holes. These spaces within the structure allows man to use zeolite minerals as filters and water softeners. In fact, industrially, they're a very, very important group of minerals. But most of the zeolites that are used in industry are not nicely crystallized specimens. It's massive material mined by the many tons. Zeolites are very common in extrusive volcanic rocks. They often form real nice quality crystals, usually colorless to white in gas bubbles or vesicles. And the common species include the minerals stilbite, heulandite, scosolite, mesolite. Often, because most zeolites tend to be white or colorless, identifying them can be very kind of difficult for newcomer collectors. But by studying the literature and looking at a lot of specimens, they come, not too bad to identify visually, at least the common species. The first locality we will visit is a road cut at the junction of Lewis River and Poison Creek. In the Southern Cascades, because of the extensive erosion and ground cover, you need some way to get bare rock exposed to find the zeolite minerals. And one of those ways, well, a very common one, are road cuts. This particular picture was probably taken in the late 1970s by Rudy Chernick. And with his directions, I visited the locality in 1983. And right in this zone right here, Rudy said to me that no, these cavities are mostly small and get crystals up to an inch, but there's small little breccia or fractured areas within the volcanic rock. Well, it turned out one area turned out to be a plug in front of a very large crawling cavity. And it had quite a lot of nice specimens of stilbite. This picture is one of the better specimens. That stilbite crystal on the right is about an inch and 2 inches in length, and the whole specimen is about 2.5 inches across. The roof of this cavity had nicely scattered stilbites on intrusive heulandite crystals. The floor had tightly compact stilbite crystals growing on it. And that tends to be the way of a lot of cavities you see in zeolites and other minerals, where the floor areas tend to be more densely crystallized and the roof areas tend to be lighter in the crystallization. At this Poison Creek Lewis River Junction, I've also found heulandite crystals scattered on the rock matrix. Those are about 3/8 inch across, and The light coloration is due to iron oxides in the matrix leaching up into the Hielandite. Another road cut in the South Cascades that produce some really exceptional zeolite specimens, the 5700 road cut in the South Fork of the Toutle River. You'll notice in the background there, that is Mount St. Helens, and it is real close to this locality. Luckily, the locality is due west, so it's out of the blast zone. But looking at the picture, all those trees are removed by logging. And the process of logging, they created this road cut that goes along through here. And all along this road cut for, I don't know the distance, maybe quarter mile or so, you could find large vesicles and cavities with different zeolite species in them. And some of these cavities produce exceptional sprays of scolecite crystal and stilbites up to 4 or 5 inches. This picture shows a close-up of the road cut. Actually, the road is over here, and here's the cut. Now, a lot of this debris and boulders right in here, I suspect was natural coming off the cut, or the timber companies left a lot of it here, and they may have used this rock as rip rock for fill in the road. But you can see white blotches in the rock right over here and everything. Those are just massive blotches of the zeolite minerals in the rock, indicating that you have pretty good mineralization there. And this slide amply demonstrates what can happen when collectors are collecting a locality and meet up with their friends. End up spending more time talking and visiting and doing the hard work of collecting. In this picture on the left is Lanny Ream, with the back in the red t-shirts, Don Howard, and then John Lindell, and then myself. This is taken probably mid-1990s. This is a specimen of scolecite from the 5700 road cut. That specimen is only about 2 inches across, but I really like the form and how it photographed. My understanding is they got specimens with sprays up to 4 or 5 inches. But these cavities were fairly close to the surface and underground weathering and oxidation, so they're very difficult to get real good quality scolecite sprays out. They tended to break up. It's the Hielandite crystal from 5700 road cut. That specimen's about 2.5 inches in length. Large Hielandites are fairly unusual in zeolite cavities. South Cascades are usually druses. The first zeolite formed when they're lining the cavities. But 5700 road cut produced some nice large ones. Stilbite crystals, it's only about a 2.5 inch across specimen. Came out of a cavity I collected there. The cavity was lined with mordanite, very fine needles of the zeolite mineral. And the stilbite, it grew around all the mordanite. So that particular specimen is heavily included in mordanite crystals. Kind of gives the textured look to it. The 5700 road cut today is pretty much very inaccessible. In the mid-90s, it took 4-wheel drive vehicle driving up steep roads to know where you're going. I believe those roads in that area are all blocked off, and the Weyerhaeuser now has very stringent rules and requirements if you pay a large amount of money to get a permit to go on their lands. In the mid-90s, Rudy Chernick, whom I've done a lot of collecting with, decided he wanted to find an old locality that John Coles had found in the 1960s. John Coles was a organ collector and extensive collecting of zeolites in that area. And he found a locality on Signal Peak, which is just north of the Toutle River, due west of the 5700 road cut. And the John Coles find was real nice stilbite crystals on matrix. So Rudy and I decided to try to find that location. And we get to these logging roads that are in that area, and Rudy says, "You can drive your truck down that road." And I go, "Uh-oh, there goes my paint job." Heavily overgrown road. We found this rock outcrop, and you can see there's a lot of vegetation growing on the rock. This basalt andesites, they weather real easy. They support vegetation growth. And it doesn't take too many years for a nice road cut full of looking zeolite cavities to turn into something that doesn't look like there's anything there. And this kind of illustrates that. But I'm breaking some rock off of it. and managed to find cavities with good, fresh, still bite, some heulandite. We also found some nice mesolite crystal sprays at this locality. This is a picture of a specimen that John Coles found when he was in there in the 60s. And what we were looking for, these very nice still bites, highly elongated, scattered on matrix pieces. That's about a 3-inch across specimen. And if you were to try to go find that location today where we were there in the mid-90s, there's probably not a road there. It's just probably a forest of trees that are 20, 30 feet high. That's how fast the vegetation grows there, and it's just phenomenal. Another area where you can find rock exposures in Southern Cascades is rock quarries. This area is heavily logged by timber companies and lots of logging roads, and they needed riprap rock to build their roads. This is the 200-237 road quarry at Wolf Point. We commonly call it the Wolf Point Quarry just for shortcut. And that's Rudy up there doing his thing, finding good specimens. This quarry was the specimen producing potential for this quarry was discovered in about the mid-90s, and found nice still bite crystals, scolecite, not very large, cavities weren't very large, but very interesting. What this quarry produced a fair bit of was some unusual zeolite minerals and unusual formations. For example, they found epistillbite twins, parallel growths of different zeolite minerals. This picture is of scolecite crystals, right there growing a cavity, and it's about 1 inch long. And this cavity here is scolecite crystals, of which they're starting to lay down. We found cavities where one side of the cavity scolecite crystals are upright, and then as you progress through the cavity, and this cavity could be 1/4 inch across, the crystals start laying down to the other side of the cavity. You just have parallel growths following the wall of the cavity. Very reminiscent of Mount St. Helens blowing down all the timber in its way. So very unusual. A little bit later in the 90s, we found the very rare zeolite mineral buglewurlite in this quarry. It's nice, well-formed crystals up to a couple millimeters. So another area where you can get good rock exposures in the Southern Cascades, or actually even the lowlands as well, because the same rock formations extend there, is construction projects. This particular one is the Skookumchuck Dam. Construction was started in 1969, completed in 1972. This basically shows some of the high wall area here. And actually, it looks like maybe a cavity here. Anyway, when they're cutting and blasting these walls for the dam, they uncovered a whole series of large cavities lined with very large mesolite sprays. And at the time, some of the world's best quality mesolite crystals came from this dam construction site. Being an active construction site, there was no public access whatsoever. Luckily, the project geologist was Charles Trantham, who wasn't active in the mineral world. And he actually collected a bunch of specimens and managed to save a lot of them. Rudy came to know him and acquired a lot of the specimens he had from Chuck, as they call him. And actually, Rudy indicated one time that he was able to get in there and do a little bit of collecting himself. This picture I was kind of like, I'm not sure who that collector is on the ladder, but this is in the spillway area, and that area produced exceptional specimens of stilbite, heulandite, but none of the real large mesolite crystal sprays. I've always liked that because that's a pretty intrepid collector up there on that very leaning ladder. This is a sample of some real fine-grained mesolite crystals. Each one of those needles is about 1 inch long. Specimens like this, if you're to touch them, you've damaged the crystals, but it's going to get its revenge on you because those needles will go right into your skin. And I know from experience, they're hard to get out. This is a picture of a small specimen of the larger mesolite found in Skookumchuck Dam. They found these highly elongated crystals and really nice sprays there. This is just a small cluster of them. It's about 3.5 inches long. And each individual crystal there is over an 1/8 inch width. And they found them up to a 1/4 inch width. So that's a big difference from the fibrous one you saw on the previous slide. This is a sample of the stilbite crystal. Nice, fairly elongated stilbite crystal. That's 2.5 inches long on a matrix of heulandite crystals. Again, here's the classic case where the heulandite is very small druses. Typically, it's formed first, and then you got stilbites growing on top of it. Skookumchuck Dam produced some exceptional specimens of that kind of material, and as well as even analcime crystals and other zeolite minerals as well. About 25 years ago, Rudy and I decided to drive up there and see if we could see anything. Is there still anything collectible up around Skookumchuck Dam? So we drove up that valley towards where the dam was, and we didn't see the dam, and I didn't see a single rock. It is a very green valley. So the next location we'll visit is a little further north, the Green River Gorge. This is in the Black Diamond area, east of Auburn, fairly close to Seattle area. And the Green River Gorge exposes a deposit which 1872 was staked for possible cinnabar mining, which are a mercury mineral, but nothing ever came of it. And in the 1950s, they tried to do it again. On this side of the river is what's known as the Royal Reward Mine, which was developed looking for cinnabar. And on this side it's called the Oakley Coal Mine, I believe. And I think they prospected this dark seam for coal. Well, this is a white sandstone, and that's just a shale coal-like rock. I don't think this ever produced anything looking like coal, but they had their hopes. This picture is showing a couple of collectors. I believe these are some collectors from Snohomish in the early 70s, removing some rock from the dams, the Royal Reward Mine side of the river. And the red material is realgar. And supposedly there were cinnabar pods associated with these things, because that's what the miners were looking for. But in reality, it's much better for its arsenic deposit rather than mercury. They were trying to break off blocks of the sandstone where the seams and fractures were lined with realgar. And where these seams and fractures would open up a bit, they would often be calcite filled. And Bart Cannon discovered in 1969, I believe, that by etching out the calcite, you could obtain a very nicely well-formed realgar crystals, some of them quite large size. And at the time, they were considered some of the best in the world. I always looked at that picture and then wondered how those guys ate their lunch. This is a picture of a realgar crystal on sandstone from the Green River Gorge. The largest crystal is about 1 inch long. It's been etched out of calcite. In the early 70s, there was a lot of rockhounds, collectors believed that they could protect their realgar from disintegration by spraying lacquers, whatever, on them. And you find old-time specimens occasionally, and you look at the surface with a loop, and it's got something sprayed on it. In reality, that didn't really do anything. If you store your realgars in darkness, they seem to retain their original quality and don't disintegrate at all. This is a specimen picture I really like. These are fairly small crystals, but I really like the gemminess and the color contrast. Those are maybe 1/4 inch or a little bit more in length. They haven't been sprayed, treated, just stored in the darkness. And the whole specimen's maybe about 2 inches across. So next we're going to go explore the Snoqualmie Pass area, a very well-known area in the state. Let's see here. We are first going to visit Mount Tenerife. And Mount Tenerife is characterized by a fracture zone and metamorphosed volcanic rock. It's called a breccia zone. And that's where you get an awful lot of rock fracturing in a very small area. And a lot of pore space is created between the fractured pieces of rock. And in that pore space, you get good quartz crystals growth from hydrothermal solutions. So after we leave Mount Tenerife, we will go down over into this area, which is Hanson Creek, which has become very well known here in recent times. Then we'll go up to Denny Mountain. And then afterwards, the last two locations we'll look at in this region is the Spruce Claim and the Pedro Claim. This is a picture of Mount Tenerife. This picture actually is courtesy of Toby Sang, who sent it to me. This may be 8 or 10 years ago of what Mount Tenerife looked like. Last time I was there in 1990, this was more of a vertical wall in here, and it was starting to get undercut. Now my understanding is a very large cave there. All that rock has been removed by collectors breaking into the rock, trying to find quartz crystals. This is a picture of looking into a cavity on Mount Tenerife. You can see the rock around the cavity. This is a metamorphosed volcanic rock. You had to use hammer and chisel to break the rock. It's fairly brittle, but you had to remove the rock around the bulk of the cavity and the specimens you wanted in order to get any kind of matrix specimens out. So it's a fairly tedious process. In the center of that cavity is a quartz crystal that's twinned along the Japan law twinning. This picture shows the quartz Japan law twin from Mount Tenerife after it's been removed from the rock mass and after it's been cleaned iron oxides. Japan law twins are typically quartz crystals twinned regular. They call it a law because it's the atomic structure is a very consistent pattern in these twins. This axis of inclination on this one is 84 degrees. They tend to be flat and tabular. And interestingly enough, they also tend to be larger than their neighboring more normal quartz crystals. That particular twin stands about 2 inches high and the other normal crystals are 1 inch or less. The next location we will visit is Hanson Creek, south of I-90. The Hanson Creek been well known for a long time. It's a couple of logging roads on the side of Humpback Mountain, and in the dirt banks of these roads, occasionally we'll find quartz crystals. In reality, the deposit is basically just a breccia zone or a couple of breccia zones up there that have been weathered and altered and slumped down the mountainside. So the crystals are just found loose in the soil, and occasionally you would find blocks of rock or the original breccia, and you could actually find cavities in those crystals. This particular picture was taken in 1979, and there's myself, and that's actually Bob Jackson, thinking that maybe 1st of November is a good time to go digging up there. We actually didn't find much of anything that day. But this is what's now known as the Banana Slug Claim, and it's on the second high, the higher of the two logging roads. And unfortunately, in the mid to late 90s, people decided they were going to stake claims to these crystals and try to keep people off the claims. And I say unfortunate because a little bit of editorializing, this is a great place you could bring a family or kids and dig and show them like finding quartz crystals. And when they stuck these claims, this particular spot is totally off limits now. And in fact, they don't even like people walking up that road. Currently, people are going up on a lower road, hiking to the end of it and going up into the woods. And there's claims up there too, but there's an awful lot of digging and collecting going on up there. In fact, I've heard it's a 3-ring circus. This is not a typical amethyst crystal from that Banana Slug Claim. This is a fairly large one, very nice, clean, with no damage. It's about 2.5 inches tall, found in the late 1970s. This is a sector from there. I really like this sector. It's about 2 inches tall. You will note, if you look carefully, you can see sparkle inclusions at the top. These are needles of the mineral hematite included in there. Most of the sectors I found in that zone, would have the amethyst coloration, but not those needles in it. So very few of them had those inclusions. Also found at Hanson Creek, earthite pseudos after pyrite. The largest pyrite crystal there is about 1/2 inch across. And you can see that the other quartz crystals with pyrite, they're pretty small. So that banana slug claim did not really produce any larger quartz crystals, except for if you're lucky to find a larger amethystine one. Now we move on to Denny Mountain. Denny Mountain is on the north side of I-90. This picture is showing Denny Creek at the bottom and this talus area, a little gulch that goes up the side of the mountain. My first memory of that gulch goes back to the early 60s. My parents brought myself and my brothers up there, and I do have memories of playing around in this lower gulch area right here, finding nodules of magnetite, thinking that was the coolest thing in the world. We also thought that the creek was fun to play in too. If one were to hike up this gulch, go up, around the corner and further up, you will come to a small cliff area, which you can scramble around on rock ledges. And pretty soon you're greeted by this site. This is a pretty important slide in my mind anyway. The deposit on Denny Mountain was discovered by Arthur Denny, one of the founding fathers of Seattle, in 1869. He was hiking in the area and he noticed these big red stains on the walls. Hiking up there, he discovered that there was magnetite deposits up there and staked it as an iron claim. But the red streaks are actually caused mostly by the rusting pyrite. This canyon is basically, I believe, formed from a fault. It eroded easily along the fault that cut across a skarn zone. And you can find in both wall areas grossular garnet, massive grossular garnet, epidote, hematite, typical skarn mineralization, as well as chalcopyrite, pyrite, and magnetite. This picture is kind of deceiving as well. The canyon is not level. It pitches upward about a 45-degree angle. Those walls are 200 plus feet high, loose rock on them everywhere. The narrowest places in that canyon might be 15, 20 feet wide. In the winter, that thing fills up with upwards of 100 feet of snow. And in the early spring and summer, you get these large snow bridges under them. I have heard stories of upwards of 10 rockhound / mineral collectors being killed up there. And one of the big reasons is they go under those snow bridges and then they collapse. If one were to go up there, you definitely want to have a hard hat. Every time I've been up there, which I'll admit was more times than I should have, I've heard rock falling off the walls. I've been hit on the head a couple of times by small rocks while wearing hard hats. But if you were to climb up through this canyon, through all this debris, which by the way changes every year, you'll come to a cliffy section at the head of it. You got to climb up in a small waterfall and then make a tricky traverse to the left, and you enter a side canyon that goes up to the left. At the head of that cliff area, the waterfall you just climbed up, there's another side canyon that goes to the right. Side canyon to the right also has quartz deposits in it and large cavities, and actually some finds have been made fairly recently up there. But for the purpose of this talk, we will go to this left side canyon, and now we're above that tricky traverse and waterfall looking down to the main canyon. You can see it's a rather intimidating spot. It's a lot more fun in the fog and rain. Turning around looking the other way, you see the little alcove area. This is the zone where the scepters have been found. This is a vertical rock here, wall here. Here's the canyon, keeps going up to the top of Denny Mountain. And there's a large cavity weathered out. I don't know what was in it because I've never been there. This area right in here was worked out by collectors looking for cavities. Originally, when they found the scepters up here, there was a large hematite vein, and the scepters were found in cavities associated with that hematite vein. You can still see a lot of hematite in this debris, but there's no trace of that vein anymore. And this area has seen extensive work in several commercial ventures as well, trying to find the scepters. In the 1970s and 80s, if you did not feel like working yourself to death here and just look carefully in the debris, you could occasionally find scepters. There's a picture of a typical single scepter that you could find in the debris. One difference is this one is very nice termination. Usually the ones in debris have a little bit of damage associated with them. And unique to Denny Mountain, well, not unique, but common characteristic of these red platelet inclusions. Originally, these were called lepidocrocite, but analysis has showed they're just all hematite. Particular crystals, maybe 1.5 inches long. This is a favorite one of mine. That's about a 3-inch long scepter. The number of inclusions sometimes range from hardly any, very pale coloration, to dense included quartz with hematite. This crystal is so heavily included that in reflected light, it looks muddy brown color. But with transmitted light through the crystal head, you get this deep, rich red glow to it. Denny Mountain has produced other kinds of quartz as well. This is a quartz Japan Law twin. I found this in an area called the Twin Zone above, near the top of one of the cliffs. That's about maybe 3 inches across from ear to ear. Quartz is etched, but a very nicely well-formed twin. I've seen and heard of twins being found up there that are over 1 foot across from ear to ear. So going north from Denny Mountain, I'll go over the valley or the mountains down in the valley of the Middle Fork of the Snoqualmie River. And that area is a little bit different in that there's a lot of claims in there from mining companies doing a mineral exploration. And their belief is there's potentials for a large-scale porphyry copper deposits up in the Middle Fork. Well, mining of that will never happen because of the wilderness area and various rules and regulations. But associated with those large-scale porphyry deposits are a number of breccia zones, which for the collectors is real interesting because they can produce quartz crystals. This is a picture of the spruce claim, a real famous claim there. Commercially mined for specimens from about 1977 on. My understanding now it's owned by a group of collectors. Bob Jackson did the bulk of the mining up here for several decades. And this was taken by mid-1980s. And you can see that all these are cavities. All the way up, this is the breccia zone, heavily fractured rock. This exposure was from Bob Jackson's work every summer. These caves up here literally crawl inside pockets. You notice here's the fault that bounds one side of the breccia. You can see the rock over here is not fractured. It looks like it's just solid granite. And it's not brecciated. Spruce is very, very famous for large quartz pyrite specimen. Specimens weigh up 100, 200 pounds each. Pyrite crystals 4 or 5 inches across, quartz crystals 2 to 3 inches long. Produce scepters, Japan Law twins. World famous, pretty much most collections probably have spruce pieces there. My spruce specimens are extremely modest. This is basically what I found up there after Bob Jackson left for the year. And he didn't care if we went up there and poked through his worked out pockets. Probably my favorite is fairly small specimens, about 2 inches high. This is a full floater pyrite crystal with quartz crystal on top of it. Another pyrite quartz floater specimen. It's a little bit bigger, that's 3 inches across. So further from spruce, about a mile to the east, is another breccia zone that's produced an interesting specimen, is the Pedro claim. This is also a breccia pipe. It's also exposed on the cliff face. Now, there's some big differences from spruce. One of those is a lot harder to get to. You've got to climb up about twice as high than spruce, and the route is less defined, and while you're hanging on to bushes part of the way. Pedro is also, mineralization is a little bit different. It's more complex than spruce. And, spruce is dominated by quartz and pyrite. Pedro has quartz pyrite, but also quite a bit of chalcopyrite, galena, sphalerite. And I have found up there even some secondary crystallized minerals from the alteration of those chalcopyrites, galena, etc. There's Pedro's character. It's got several cliff faces. This is the lower cliff face, which my collecting partner in the early 80s, Donald Stalder, is there on the cliff. And you really couldn't see any pockets here because basically they're mostly covered up with iron oxides. And so it's kind of not productive for people collecting on the surface here. You go above the tree line here, and there's a second area of cliffs where they were actually doing a little bit of commercial collecting there in the early 1990s. This is a Pedro chalcopyrite crystal. It's about 1.5 inches across. Found it in a cavity that was opened up and worked out basically, but there's still some good specimens in it. It was covered with iron oxide coatings, and I flaked them off. And what are those little red things? Oh, little microcuprite crystals on it. And then I threw it in, but it's on the still had iron oxides on it, so I threw it in some hydrochloric, and it came out with this beautiful luster on it. So that's the way this particular specimen is. I did save some of the cuprite samples from other crystals from that same pocket, though. The pyrite up there is, I think, a lot more interesting. Not all of it's like this. There's quite a bit of variability. But this particular specimen, this is actually a single cubic faces from a single cube. And then the pyrites on this surface here, instead of developing a single face for unknown reasons, decided to develop this very Hopper parallel growth pattern, and made for a very striking specimen. And I've seen multiple specimens of it like that from Pedro. So going north from Pedro, now we're on the only locality that in this park anyway, along Stevens Pass Highway, is the railroad cut at Sunset Falls. This is almost, you would call this a non-locality, but it did produce some really good quality specimens. This picture was taken in the early 1980s. Again, that's Don Stalder there with his young daughter. And the railroad cut there at Sunset Falls exposes these boulders of granodiorite from, I believe it's the Snoqualmie granodiorite. Anyway, in the granodiorite, there's these myrolitic cavities that were exposed. And within those myrolitic cavities, they found exceptional specimens of sprays of epidote crystals, apatite, I believe a single scheelite crystal was discovered, as well as microcline smoky quartz. The problem here, and this was in the late 70s, my first time there, all I could find was the microscopic scraps that were left. You basically can't do anything there because, you can't put a bar in and move those boulders, because right out of the picture here is the railroad track, and it's actively used track. Every time I've been there, at least a couple of trains have gone through at 40 and 50 miles an hour. So it's a big deterrent to really doing anything there. This is a specimen of epidote sprays from the Sunset Falls. That specimen is about 3 inches long. So quickly moving, because I see we're getting short on time here. Going north from the Stevens Pass area, we go up to Vesper Peak, fairly well-known area, skarn zone near the top of the peaks, producing exceptional quality garnet specimens. I spent a good part of my working career sitting in an office building at Boeing, and I could look out the window and see the top of Vesper Peak. This view is looking to the east. Monte Cristo is in the basin area here. The trail to get up there from the Monte Cristo Highway, you have to go up the side valley there through a very narrow notch here, across this talus, and then very arduous hike, something like 4,000 feet of elevation gain in 3.5 miles, 4 miles, but very scenic once you got up there. Here's a picture of the deposit at Vesper Peak, and there's actually the summit of Vesper Peak. This is a skarn zone, iron oxides, basically mostly Hedenbergite. You get cavities up there with Hedenbergite crystals. But what's the collectors desired was the grossular garnets that would occur in these cavities as well. This locality has seen commercial collecting in the, I know at least in the late 70s and early 80s, and then in the early 70s too, pardon me. It was initially discovered and claimed that at least I can find in the history in 1949. So there's a long history of this locality. Currently, it is still being worked, held under private claim, but I understand they're not finding many good specimens anymore. Bart Cannon worked this in the 1980s, and from my understanding, kind of considered it worked out. This is a specimen that came out in the early 70s. It's about 5 inches long by about 2.5, 3 inches wide. And these are nice grossular garnets, transparent, highly lustrous. Vesper peak garnets are well known for cubic faces as part of the morphology of the crystals. And these are quartz crystals. And it's probably my favorite Vesper specimen I got from Bart Cannon when he was doing his work up there in the early 1980s. Nicely shows the cubic face right there. Nice transparent, good color crystal. And this crystal is about a 1/4 inch across on Hettenbergite crystal. So the last locality we'll visit in this tour of the Cascade Mountains is going to be the Golden Horn Batholith, which is along the Highway 20 in the North Cascades. This is a different kind of a locality than the others that we have visited. The Golden Horn Batholith is a true granitic batholith, and it's considered a per-alkaline granite. It's actually made of 4 phases granite. There's 2 biotite granites. There's what we're calling a border granite, and then there's the per-alkaline granite up there. And this granite, the per-alkaline granite, it's characteristic because the content of the rock, the sodium, calcium, potassium content, exceeds the amount of aluminum in it. And that makes a big difference in what minerals are formed in it. The Golden Horn Batholith was also formed at fairly shallow depths, and so allowed the formation of myrlitic cavities. Most granites form fairly deep, and the pressures prevent those formation of those cavities. As well as the cavities in the Golden Horn were also enriched in trace elements, lithium, zirconium, rare earth elements, and some other elements as well. So you end up with a suite of minerals found in these cavities that are quite unusual, and a lot of them are very rare. This picture is what we're calling the road cut, which is a couple miles east of the actual Washington Pass. When the highway was built, this road cut was made, but it was very unstable, and it's still unstable. Debris falls down continually, and the road crews take that debris off the road and push it over the side. And then you can see down below these original boulders that are gray color match the color of these boulders. These were there before the highway was constructed. This is all new debris. Well, after the highway was constructed, and for a period of a decade or two, it wasn't too difficult to find fairly large cavities over 3-4 inches across with larger crystals in them in this area. But in the ensuing decades, because of heavy collecting pressure, it's very difficult to find any large macro specimens up there. But there are literally millions of microscopic sized cavities in a 1/4 inch and up there. And they have excellent quality crystals of different micro species. And so this area is today still would be productive of finding rare and unusual crystals and minerals, only they're typically microscopic size or maybe a little bit larger. This is a picture of a typical per-alkaline granite boulder at Washington Pass taken at the road cut area. The brick red mineral is elpidite, and you got arfetzinite here, which is the dark mineral in this per-alkaline granite. This area probably once was maybe the site of a cavity, and then it was exposed and then tumbled down the side of the mountain and the road cuts. So there's probably a few crystal faces in here, but it's mostly just some fairly coarser granite showing the elpidite mineral. Elpidite is fairly rare mineral on a worldwide basis and pretty much found only in per-alkaline granites. This picture shows a typical myrlitic cavity found in the biotite granites. The biotite granites up there don't have as many of the rare minerals in there, but we are finding a few unusual minerals within the biotite granites, including some rare earth carbonates. Quartz crystals up to about 1 inch, microcline crystals. The crystals, if this cavity wasn't exposed to the sun for many eons, these would probably be a darker smoky color, but they've been weathered sufficiently, so they're just kind of colorless. Most of the quartz found cavities at Washington Pass, especially the larger cavities, tends to be etched It can be very dark in color, but the surfaces are etched and they're not brilliant. In the arfetzonite granites in the road cut area, though, you can find quartz crystals that are just brilliant, very high quality luster, but of any size, they're very scarce. I have not found that many in the, I've been collecting up there since since 1977, and it just haven't found that many of this quality. This one has arfetzonite crystals growing out of the side of the quartz. It's about 3 inches long. This is an arfetzonite crystal on microcline. This is only about maybe a 1/4 inch long, and now we're looking at a few pictures of what can be found in these small cavities and microcrystals. And from my perspective, this is where the big excitement of Washington Pass is, at least in the last couple decades. Is looking at these rare minerals, the microscopic rare minerals in these small cavities. Again, that thing's about a 1/4 inch long, arfetzonite crystal sitting on microcline. This one I particularly like. The yellowish crystal on the left is a zircon crystal, and then you got a chain of fluorite crystals going across, and it always reminds me of a caterpillar deciding he's got a zirconium deficiency. That specimen might be 1/4 inch across the whole frame picture there. So this is very definitely would be considered a micro, but some of those micros up there can be very attractive, brilliant colors, and very interesting. This is another fairly rare species found up there. In fact, this is very difficult to find up there. It's genthovite, found in the biotite granite, and again, it can be very, very difficult to find. Genthovite is an unusual mineral. It's a zinc, beryllium silicate with sulfur in it. Quite an unusual combination. It was also fairly recently found up there and described, considering the other minerals. Here's one of our token rare earth minerals. The title of the slide is calling this synchesite. I did that for simplification purposes, and the fact this specimen came off of Liberty Bell Talents area, and a lot of those tend to be dominant in synchesite. More appropriately, you should call this a rare earth carbonate, because rare earth carbonates are common at Washington Pass, and they commonly are intergrowths of synchesite or bastnasite. Both synchesite and bastnasite are group names, and so it can even get more complex. And this boulder, they can look different than this boulder and then this boulder, and their chemistry can be different. So in actuality, to really accurately know what it is, it needs to be analyzed and for that boulder, and then we know what it is in that boulder. Better than say it's the same thing in the next. And you go online, Mindat, and look, and you got people calling them all sorts of names like they think they've got the answer for it. And unless it's been competently analyzed, we really don't know what that is. This is a very interesting crystal because of all the zoning on it. You could easily have synchesite on the outer zone and bastnasite on the inner zone. And this oscillatory growth pattern is actually kind of unusual. It is common up there to find white hexagonal tablet-like crystals up to a couple millimeters. But this kind of growth is very unusual. So what really put Washington Pass on the map worldwide is the discovery of 3 new species up there, especially the first one. Late 1960s, Bart Cannon discovered this interesting mineral up there and looked at it and said, oh, it must be morganite. A fairly large crystal, kind of pinkish, sort of hexagonal looking. Work was done on it, and by 1977, they decided that new species, and the paper was published. Zechsterite is lithium, sodium, zirconium silicate. One thing that's very unusual about it is it formed very large crystals, which is unusual in the world of new species. Usually there's microscopic things or thin sections where you can't see anything. But these zechsterite occurred as large crystals up there, as well as massive in the rock. Second new species found is Okanaganite-Y, found by Bob Boggs published by Russ Boggs. It's a rare earth borofluorine silicate, complex crystals. Zechsteroid's fairly common at Washington Pass. Okanaganite, fairly scarce, though it's widespread in the orphitzonite granite. And then you've got calciolerite, 1988, again discovered by Bob Boggs and described by Russ. And that's a calcium zirconium silicate. This picture is showing Marcus with his trusty black light looking for zechsterite. You'll notice, interestingly enough, that there's a rock over his head. This spot is kind of in the high country, and we're actually in a cave formed by a very large flat boulder resting on other boulders here. And he wants to check out that surface and see if there's any zechsterite there. And by putting a small fabric tint over it, turning on the black light, all this fluorescent material is zechsterite. Zechsterite has the very helpful characteristic of being fluorescent in shortwave UV. This is basically masses of zechsterite and probably broken crystal faces. And these are just a series of small cavities here. The rock is fairly hard there. I don't think we got a specimen off of that, but it sure made a nice picture. And today, it is a very popular activity for collectors to go up to the road cut area at night with black lights and see if they can find pieces of zechsterite or fragments of zechsterite crystals in the road cut. This is an actual picture of an inch-long zechsterite crystal found in a cavity in 1983. The crystal itself is about an inch long. Very nice crystal, translucent. There are transparent areas in there. This is what everybody wants to find out there. These days, finding large cavities with good quality zechstrites is almost unheard of, though there has been stories of recently a fair find of some nice zechsterite up there, but I don't think that the quality was like this. This is a picture of Okanaganite. These nice tetrahedrons forming a chain, fluorite crystals here. From the Okanaganite boulder that I found in the late 70s, that chain is about a couple millimeters long. Okanaganite is found widely scattered in orphitzonite granite, but it is not common, and since it occurs in microcrystals only, a lot of collectors overlook it. Calciolerite, found only on Liberty Bell. Again, microcrystals. This may be less than a millimeter here. There's these blocky white crystals here and here. But you notice that the color is real similar to microcline. And unless you're really aware of it, you know what you're looking at, you could easily go and throw it. Again, microcrystals. These days, Liberty Bell has been the scourge of people looking for quartz crystals and moving a lot of boulders and stuff, that they never see this stuff. So at the end of the talk, you know, one always dreams of that pot, cavity of crystals at the end of the rainbow. It's nice at Washington Pass in good weather, but you know, it's even more fun when the weather turned bad. So that's the end of the talk. Are there any questions?
Okay, thank you very much, Randy. That's outstanding overview of Washington minerals, and we wrapped up with the golden horn batholith, and our next speaker is going to go into much greater depth, and that speaker is Marcus Ratschke.